Hello everyone, my name is Osvaldo Ramos Neto and I'm a mechatronics engineering student and a researcher at the Federal University of Technology, Paraná, from Curitiba, Brazil. Today I'm pleased to present our work titled A Novel Robotic Mechanism for Efficient Inspection of High Voltage Transmission Lines. This project was developed in collaboration with my colleagues you see on screen. Our main goal is to increase safety and efficiency in a task that is traditionally high risk. The inspection of high voltage power lines is a critical task that ensures energy reaches us without interruptions. Currently, this work is largely done with helicopters and field crews, which poses a significant risk to human life and also has a high operational cost. In this context, robotics offers a promising solution allowing this inspection to be performed autonomously and safely. When designing a robot for this kind of task, we faced two major challenges. First one, the transmission lines by themselves are not smooth cables. They have various obstacles attached to them, like, for example, vibration dampers. The robot must be able to navigate and pass them without big interruptions, and after that, keep moving on the line forward. Second, stability is crucial. While doing this movement of transpassing and while on the line moving forward, the robot cannot fall. Therefore, our main objective was to create a mechanism that specifically solves the problem of obstacle transversal, ensuring safe and uninterrupted movement along the cable. To achieve the necessary stability, our design philosophy was based on a fundamental principle of physics, keeping the center of gravity as low as possible relative to the support point, which is the cable. We used SolidWorks software to optimize the mass distribution. The structure, as you can see in the figure, was built with aluminum profiles. This gave us two advantages: a robust and yet lightweight robot, and a modular platform which allows us to add new sensors or tools in the future. The robot's base houses the batteries and controllers, keeping the weight in the lowest point as possible. The robot's movementation along the line is driven by a system of three independent step motors. Each motor drives a steel pulley designed with a specific groove to fit perfectly onto the transmission cable. The rotation of these pulleys generates stable and precise linear motion, allowing the robot to travel along the line to perform the inspection. Here is the heart of our innovation, the pivot mechanism. To overcome an obstacle, it's not enough to just move forward on the cable. The robot needs to be able to get around the obstacle and transpass it. To do this, we designed a system where each of the three locomotion units can rotate 90 degrees. As you can see in figure 3, the pulleys move from the position A, that is the position for the normal operation when the robot is moving forward on the cable, to position B, which lifts up and out of the way of the obstacle, allowing the robot to transpass it. This movement is driven by a dedicated motor and a gear reduction system, which ensures the necessary torque and precision for the movement. Let's now see how the sequence works in practice. This image illustrates the step-by-step process. First, the robot moves forward until it nears the obstacle, which in this case is a vibration damper. Then, the first locomotion unit stops. Its pivoting system is activated, lifting the pulley out of the way. The robot then inches forward, supported by the other two pulleys, moving the first one past the obstacle. This process is repeated sequentially for the second and third units. At each step, the robot remains stable as that there are always at least other two pulleys firmly supported on the cable. Once all three units have cleared the obstacle, they return to their original position and the robot continues its inspection mission. The sequential movement is a key to the system efficiency and safety. The safety of the system is primordial. Despite the stability, in a way that we can ensure that everything keeps working in a safe condition, and mainly to protect the pivoting mechanism motors from excessive loads and ensuring the robot remains firmly attached to the cable, especially during the transversal sequence while the robot is transpassing the obstacle. Implemented a locking system. This system uses solenoid actuators that act as a mechanical lock. Once a locomotion unit is in the correct position, either for the operation position or the lifted one, the lock engages, relieving the load of the motors and ensuring the structural integrity of the system. In conclusion, our project has successfully demonstrated a viable solution to one of the biggest challenges in line inspection robotics, that is, transpassing the obstacles that are attached to the cable and keeping its stability. The modular structure has proven effectiveness, and the pivoting system was able to navigate obstacles safely and repeatedly. As for our next steps, we plan to integrate a suite of sensors onto the robot, such as high-resolution cameras and thermal sensors, allowing that the system will be able to actually perform the inspection. That will be possible due to the modularity of the system that allow us to adapt and make modifications without many difficulties. Furthermore, we will continue to improve the system autonomy. First, I would like to thank the IARIA Conference Committee for the opportunity to present our work. Also, my sincere gratitude also goes to our funding agencies, whose support was essential for this project. Thank you for watching and for your interest in our research. I welcome any questions and comments. Please feel free to contact me using the email address shown on the screen. Thank you.